Also, thanks for the opportunity. I hope some of the talk is interesting for some people. So, as Andrea said, what I was going to talk about is just using light scattering approaches for understanding protein-protein and protein-solvent interactions. And just a brief, as soon as I can get a brief overview, I should say these are my collaborators who have contributed to the work that I'll be presenting today. So I've kind of taken a lot of results from the last few years, and these are the collaborators who've contributed to that work. So just an overview of the talk. Initially, I just want to say a few words about the theory underpinning measuring protein-protein and protein-solvent interactions. I don't want to spend too much time on that, but I just want to make a couple points, and then I'll go over how we use measurements of protein-protein interactions to understand specific ion and buffer effects. And then I wanted to look at connecting interactions, the two-body interaction between a pair of proteins, which you measure under dilute solutions, to the concentrated solution properties. And then lastly, I'd also discuss how we can use light scattering for measuring protein-solvent interactions in terms of preferential interaction parameters. And so just a brief, this might be a review for quite a few people, but what we're measuring in light scattering is the ratio of the scattered light to the incident light, which is known as this Rayleigh ratio. When you're looking at a macromolecular solution where the correlation length of the particle size is much less than the wavelength of light that you're using. And the scattering occurs due to fluctuations in refractive index. And when you do the analysis, you write the fluctuations in refractive index in terms of fluctuations in terms of your thermodynamic variables. Here I've written it in terms of volume concentrations. You also have fluctuations due to temperature, but those only mainly contribute to the solvent scattering, and we measure the excess scattering. And so if we express the refractive index fluctuations in terms of volume concentrations, we also have these, let me just see if I can get my pen to work. We have these refractive index increments, which are measured at constant volume concentration. The connection to thermodynamic properties is made by noting that fluctuations are related to second derivatives of free energies. And so that allows us to write the light scattering equation in terms of these derivatives, which were related to Kirkwood-Buff integrals. And then there's various approaches for doing the thermodynamic analysis. The approach that we use is that we utilize is to rewrite these refractive index increments in terms of refractive index increments where the natural variables are given by the semi-grand partition function, or what's called the Macmillan-Mayer free energy, where the independent variables are the volume concentrations of your solute molecules and the set of solvent chemical potentials. And if you reformulate the light scattering equation in terms of these refractive index increments, which are derivatives of your refractive index with respect to solute concentration at fixed solvent chemical potential, then you get this equation for your light scattering equation, where you use the light scattering to determine the osmotic compressibility of the solution, or the structure factor in the limit of the wavelength of Q going to 0. And so I just raised this point because I'll come back to this point that we can use that the light scattering equation in this form is related to these refractive index increments at constant chemical potential. And so the connection then to protein-protein interactions is just made by noting that the osmotic pressure can be expanded in a Taylor series expansion, and the osmotic second virial coefficient, which is the second order term, is related to protein-protein interactions through this integral. And so this virial coefficient is related to an excluded volume contribution plus an integral of this potential mean force, which is an interaction free energy over all the non-overlapping configurations between a pair of proteins. So we can relate the light scattering to this virial coefficient. This virial coefficient then tells us about this interaction-free energy, or this average interaction-free energy. Usually we report it in terms of reduced form, which is the measured virial coefficient over this excluded volume contribution. If it's greater than 1, then we say the net interaction is repulsive. If it's less than 1, then you have some, you know that you must have some attractive contributions to the virial coefficient, because the virial coefficient is less than the excluded volume contribution, which exists in all systems. And just to make things a little more confusing, people tend to represent the virial coefficient in different units. So like when you're looking at molecular properties, you usually use the volume units. When you expand your osmotic pressure, as I did up there, you can also represent it in terms of kind of specific volume units, milliliters per gram. And when I started making these measurements many years ago, we used it and represented it in these units, which are what were used in the light scattering analysis. And so this is just when you substitute in your osmotic compressibility into the light scattering equation. And so in order to measure the virial coefficient, you look at dilute protein solutions, and you just measure the left-hand side of this equation against protein concentration and the slope. If you measure a series of different protein concentrations, the slope of the plot gives you the virial coefficient. One of the things I always tell my PhD students is that first of all, that light scattering never lies, and that if your measurement isn't working, it's not due to the light scattering, but it's due to the concentration measurement. You really have to have precise concentrations. You need to know what the concentration of the protein is in the light scattering cell. So the types of systems that we use, we have kind of multiple ways of making sure we have the right concentration. We use kind of a precise system, a very precise pumping system, so that we can calculate concentrations from dilution factors. And we have a variable path length UV cell, so that we can also measure the protein concentration online. So we spend a lot of time just trying to make sure we're measuring the correct protein concentration. And then what we do is we interpret the measurements using relatively simplified models, at least to start with. And so for the interaction potential, we always have an excluded volume contribution. And some work by Chris Roberts just showed that if you have an anisotropic protein, the excluded volume contribution can be approximated by the excluded volume of a sphere that has a diameter equal to the hydrodynamic diameter of the protein. So if you use DLS to get the hydrodynamic diameter, you can use that to get an approximation for the excluded volume. And then what we do is we kind of break up the interaction into two terms. We say we have some short-range attractive term, which we don't really know the origin of. And then we have a longer range electrostatic repulsion term, which is due to double layer force repulsion. And the reason we can separate this out is just because they have a different range. The double layer repulsion is longer range than this short range attraction. And so we model the short range attraction using this sticky Backstrom model. The reason we do that, number one, is we don't really know what this interaction is. And then the Backstrom model only has one adjustable parameter, whereas if you use like a square well potential, you have two adjustable parameters. And then for the double layer repulsion, we just use the DLVO theory. In DLVO theory, the potential depends upon the charge of the protein, and it depends upon the ionic strength. So the ionic strength controls the range of the potential. So we usually use this as a starting point for understanding our measurements. More recently, a lot of people are doing dynamic light scattering for measuring protein interactions, just because the user friendliness of the experiment, and you can do a lot more measurements, or it's much higher throughput. And so when you measure from dynamic light scattering, you measure a mutual diffusion coefficient, which has two contributions. It has a contribution from your hydrodynamic interactions, and also you have a free energy gradient that causes diffusion. And so the hydrodynamic function is related to the ratio of the sedimentation velocity at a finite protein concentration over the dilute solution, infinite dilution sedimentation velocity. And at low protein concentrations, You can define the sedimentation interaction parameter, which relates to the two-body hydrodynamic function. And then you can, from the diffusion coefficient as a function of protein concentration, you can determine this interaction parameter Kd, and it's related to both a viral term from the structure factor, which is related to the second viral coefficient, and then the sedimentation interaction parameter. And then for spheres interacting through short-range isotropic potentials, there's an analytical solution for the sedimentation interaction parameter, in part from Batchelor, and then also you can determine if it's a short-range attraction, you can determine the contribution of the short-range attraction to the sedimentation interaction parameter. And so for these simplified systems, there does exist a correlation between the second viral coefficient and the interaction parameter Kd, and that's given by this solid line. And we've shown that this prediction using this spherical model actually does agree with data for an antibody. If you go to very large values of the viral coefficient, then you start having double layer forces, and then there is a solution for the effect of double layer forces on the sedimentation interaction parameter as well. So we can use these for simplified systems. We can use both the Kd and B22 measurement for measuring interactions. And so here I just show how interactions depend upon ionic strength and pH. So usually if we want to understand a system, we always measure the behavior as a function of pH and ionic strength. And at low salt concentrations, we try to interpret in terms of DLVO theory. And so for this MAB, it has a high isoelectric point, so you get the strongest repulsion at low pH when the MAB has a lot of charge. And when you increase pH at fixed ionic strength or fixed screening length, you see that the interactions become, repulsive interactions become weaker, and you get attractive interactions. And when you increase ionic strength, you screen the repulsive interactions, and you end up at high ionic strength, you only see a very weak ionic strength, a very weak pH dependence, and that's because you've screened the electrostatic interactions. The other thing to note here is that when you approach the PI, you get these attractive interactions that get weaker with increasing ionic strength. At low salt concentration, the main effect of ionic strength is to alter electrostatic interactions. So this implies that you have some electrostatic attractions that you're screening. And this just occurs in a simplistic way. You could interpret this as saying that you don't have a net charge in the protein, but you do have oppositely charged patches which can interact with each other and give rise to these attractive interactions. And these types of interactions have to be anisotropic interactions because they're due to charged patches on the protein surface. And so for this particular system, we looked at how well DLVO theory could work. And so what we do is we can fit the ionic strength dependence of the second viral coefficient at a fixed pH. We fit the ionic strength dependence to determine a charge parameter. And you find that the fit value of the charge parameter to capture this ionic strength dependence kind of agrees with what you would expect if you did calculated the charge in the protein based upon the pKa values. And so it does seem like the DLVO theory does work relatively well to explain the behavior of this particular MAB. And then we also then use this kind of model to understand effects of buffers. So I was working in a formulation development group where they need to choose between different buffers. And one thing is that you want to avoid aggregation, and aggregation in part relates to the colloidal stability. And so we're looking at whether or not the buffers impacted the colloidal stability, which is in part related to this electrostatic repulsion. And so what we did is we chose the buffer concentration such that the ionic strength of the solution was 25 millimolar. So in this case, we're going to have the same screening length. Within DLVO theory, then the only difference in these solutions would be the effective charge on the protein molecule. And you can see that when you go from acetate to succinate to citrate, you really reduce the protein-protein repulsion. And this is also going from a monovalent buffer to a divalent buffer to a trivalent buffer. And so what's happening here is that the buffer, you could interpret the buffer effect as binding to the protein and reducing the effective charge on the protein surface. And when you increase the ionic strength of the solution, you see that you screen this effect, which is what you would expect if it was a strictly electrostatic interaction. Here we increased the ionic strength by adding sodium chloride, but we've also increased the ionic strength by adding the buffer itself. And you do see a similar pattern. So it does look like the main effect of the buffer is to bind to the protein and alter the effective charge on the protein. At pH 6.5 with a citrate solution, you can actually see that you invert the charge on the protein surface, and the protein behaves like it does at the isoelectric point, where you get these attractive electrostatic interactions. And so it could be that the citrate, because of its -3 charge, does bind, and then you have patches of negative charge to interact with patches of positive charge in a simplistic way, if you want to interpret the behavior. And so we also verified this just by doing zeta potential measurements. And so we measured the zeta potential in these different solutions with the different buffers. You find a strong correlation between the zeta potential and the KD. And so this implies that the KD does really reflect these electrostatic interactions at the lower ionic strength conditions, and supports the conclusion that the buffer is binding to the protein surface and altering its effective charge. So another effect, after we looked at the buffer effect, we wanted to go back and revisit this reverse Hofmeister series effect, which was kind of studied quite a lot around 2000. And the reverse Hofmeister effect, effectively what happens is you have chaotropic anions are able to salt out positively charged proteins at moderate salt concentrations. Usually chaotropic anions at high salt concentrations will salt in proteins. And so there's been a lot of work dedicated towards understanding this effect. And one of the findings is that chaotropic anions tend to preferentially adsorb to either nonpolar regions on protein surfaces or to polar groups on the proteins. And this is supposedly the reason that you get this reverse Hofmeister series. And one of the questions that we wanted to look at, well, how can we interpret this on the impact on protein-protein interactions? There have been a few articles where they claim that, you get the preferential absorption, and then that has the effect of lowering the effective charge on the protein, or it could also reduce the screening length. And so we wanted to look at whether or not we could explain this chaotropic anion effect in terms of strictly screening of double layer forces or changing the effective charge on the protein. And so here, what we compared is sodium chloride to sodium sulfate. We know that sulfate will bind to the protein surface because it has a divalent charge. And when you compare sodium chloride to sodium sulfate, you see at low salt concentration at the same ionic strength, the interactions are less repulsive in sodium sulfate. And that's because the sulfate is lowering the effective charge by binding to the positively charged groups. And then when you increase the ionic strength, you get rid of this effect. Or here we're actually increasing the salt concentration. And then at an ionic strength of 275 millimolar, the sodium chloride solution behaves the same as the sodium sulfate solution. And this shows that it's mainly a double layer, an effective charge effect, which is screened by increasing the ionic strength. When we looked at sodium thiocyanate, what we actually found is that as you increase the ionic strength, you do see that reduction in protein-protein interactions, but you see that at higher salt concentration, you don't screen this effect, and that you get attractive interactions even at the ionic strengths where we did screen it with sodium sulfate. And so this kind of implies that there's an additional attraction that cannot be explained by DLVO theory. This attraction could arise due to the assumptions based upon using the Poisson-Boltzmann theory within DLVO theory, or it could be some other sort of non-electrostatic attraction. And so we also looked at lysozyme. Lysozyme was kind of the model system, I think, when it comes to proteins that was used in the literature for understanding this reverse Hofmeister series. And you can really see that with lysozyme, you get very attractive interactions when you use a chaotropic salt like potassium thiocyanate. And then when you compare, say, potassium chloride to potassium sulfate, you find that there is a difference at low salt concentration, and that difference is screened when you go to higher salt concentration. So once again, you find this additional attraction, which cannot be captured by simply changing the effective charge on the protein. We also looked at the zeta potential measurements, and we do see that the sulfate is more effective at reducing the zeta potential, even though that you get a stronger attraction in the potassium thioisocyanate solution. So I think with this data, it can shed additional insight into these kind of understanding of chaotropic anion effects and how they alter protein-protein interactions. And then the other system that we wanted to look at in terms of specific ion effects is because these multivalent ions do bind to proteins, you could also ask the question, well, can you actually bind these multivalent ions to a protein that has the same charge as the multivalent charge? So we wanted to look at whether or not we could bind multivalent phosphate ions to negatively charged proteins to overcharge them and increase the colloidal stability, which should reduce the aggregation resistance. And so people have looked at engineering in overcharging effects. The negative or downside about engineering in overcharging effects is that you reduce the conformational stability of the protein, or you cause it to unfold more readily. And aggregation is caused by both unfolding and colloidal stability. So overcharging proteins through mutagenesis is not really a good strategy, because you still do get aggregation. It's just that the aggregates don't grow very quickly. And so in this case, we looked at this tripolyphosphate, and then we also looked at ATP. And we looked at ATP also because there's been some work in the recent years showing that ATP might also play a role in controlling protein self-assembly in cellular environments. And people were claiming that the ATP kind of acts as a hydrotrope, where the adenosine group will bind to nonpolar regions, and the phosphate group will kind of lead to a protective layer around the protein due to its high hydration. But we were also wondering whether or not this effect of ATP could also be related to overcharging proteins. And so in this case, we measured the zeta potential for a couple of different proteins, chymotrypsinogen and for ovalbumin. And we showed that when you compared sodium chloride to the tripolyphosphate or ATP, you could really see that you reduce the zeta potential much more readily with ATP or STPP. So you could see that these ions were binding to ovalbumin, which is negatively charged, and increasing the negative charge on the protein surface. And so here we did some aggregation studies. So once again, aggregation is driven by protein unfolding. So to study aggregation, usually if you want to study it on a reasonable time scale, you have to heat up the protein solution to a temperature where it begins to unfold, and then it will start to aggregate. And so we did these temperature ramp studies, and in this graph here, we did them with varying concentrations of sodium chloride, and you can see that when you increase the concentration of sodium chloride, you kind of reduce the temperature onset of aggregation, or that's causing aggregation to occur more readily. And this could be due to screening electrostatic interactions, because you're reducing the colloidal stability by decreasing the screening length when you increase the ionic strength of the solution. But what you find with ATP or STPP, well, the first thing is that STPP and ATP behave almost exactly the same. And so in this case, it's definitely not going to be this effect of the adenosine group being nonpolar that makes a difference for these systems. But what you see is that in a concentration range of 5 to 20 millimolar, you see that ATP and STPP are very effective at reducing the aggregation. And what's happening here is when you do the analysis, they're not actually preventing aggregates from forming, but they're really slowing down the aggregate growth rates. And really the colloidal stability is going to relate to the aggregate growth rates, not the aggregate formation rates. And so the reason I'm talking about this in this talk is that we then tried to rationalize this based upon kind of viral coefficient measurements. And so we measured the viral coefficients in the sodium chloride solutions, and then the colored symbols are in STPP and in ATP solutions, and then compare them at the same ionic strength, so that the screening length should be the same. Some people could argue that the screening length, you can't really use the Poisson-Boltzmann theory for multivalent ions due to ion-ion correlations. So we've also been looking at that effect as well. But here you do see that you get this kind of increased viral coefficient at the same ionic strength. And that implies that one way of interpreting this is that, you have some ion binding that's increasing the effective charge on the protein within DLVO theory. We could then fit an effective charge using DLVO theory. And you can see that you have a lot of binding to the protein to give rise to this protein-protein repulsion. And then what we wanted to do is to explain this minimum and aggregate growth rates that occurs around 5 to 20 millimolar. If you just look at the viral coefficients, you get the strongest repulsion at very low salt concentration, not at 5 to 20 millimolar. But the colloidal stability is controlled more by the barrier and the interaction potential at short range, which is related to this Fuchs ratio, which tells you about collision rate relative to what the collision rate would be under diffusion limited conditions. And so we calculated the Fuchs ratio using the results from fitting to DLVO theory, and you could show that this Fuchs ratio was greatest kind of when you get to this concentration range of 5 to 20 millimolar. So this kind of helped rationalize how these ions were binding to the proteins and possibly reducing the aggregate growth by increasing the effective charge on the protein. So I wanted to say a few words about calculating concentrated solution properties. So in this case, we're looking at a protein with HSA. And so HSA was a very nice model that we looked at. When we measured the viral coefficient for HSA up to high ionic strength, we found that the viral coefficient was equal to the excluded volume contribution. And then we also had some SACS data from Pernilla Harris's group, and we could analyze the SACS data, and we could show that you could fit the SACS data and get as good fits without including any attraction in the interaction potential. So both the SACS data at relatively high ionic strength and the B22 data suggested that there's no short-range attraction for this protein. So it's a very nice model system. One of the things is that when you fit it to the spherical model, the structure factor profiles, you do see that the size decreases. And so that's because you're assuming like a spherical geometry for the protein. So what we compared is fitting the structure factor data or the osmotic compressibility data as a function of protein concentration. We compared an ellipsoidal model, which reproduced the form factor for HSA pretty well, versus a spherical model. And you can see that the ellipsoidal model gives a much better fit to the data than the spherical model, which is shown in red. The spherical model kind of has much more curvature when trying to fit the data. And so if you parameterize the model based upon the viral coefficient that you measure at low concentration, you can still get a relatively good fit if you're using the ellipsoidal model, but you really overpredict the curvature when you overpredict the curvature when you use a spherical model. And so effectively, if you're going to use a spherical model for an anisotropic protein to capture the behavior of the whole concentration range, really, if you do try to parameterize it on the dilute solution properties, you're going to overpredict the osmotic compressibility at higher concentrations. And that's why you need to use a smaller size in your spherical model if you want to capture the concentrated solution data. And so then we've also looked at then trying to fit the model to a couple of different antibodies. We've looked at one mAb that I presented earlier, which looks like interacts through relatively weak interactions. And then we have data for another mAb where we get very strong attractive interactions, especially under low ionic strength conditions. And so what we did then is we have this Baxter DLVO model or the repulsive Yukawa model. And there's an analytical solution to the OZ equation for this model that we can then use to fit to the structure factor or osmotic compressibility data at up to high protein concentrations. And so what we find is that for COE3, which is the weakly interacting mAb, we can reproduce the structure factor data relatively well using this simplified interaction model. And when you fit the parameters in the model, the adhesion parameter and the charge, these values, at least the charge values, agree for the repulsive conditions with what we regress from the viral coefficient measurements. You do find that the size that you fit is a little bit smaller than you would expect. And once again, that's because when you use this kind of spherical model, you tend to overpredict the osmotic compressibility, especially when you're looking at systems that don't have very strongly attractive interactions. And then we looked at the model also trying to predict the behavior of this other system where the interactions are much more attractive. And you can see that the best fits to the model are not very good when we're using this simplified interaction model. And so in this case, what we believe is happening is that when you have a weakly interacting system, the interactions, we're modeling it with centrosymmetric interactions. Really, the interaction is never going to be truly centrosymmetric, but they're still very weakly anisotropic that a centrosymmetric model is going to work well. But when you get very anisotropic interactions or highly directional interactions, you tend to start forming more well-defined oligomeric species. And in this case, that's probably when these simplified interaction models are going to break down. And so in this case, we used a relatively simple approach to understand the behavior of the other antibody. And so what we did is we just postulated the existence of dimers or trimers. And then what we could do is we just fit a multi-component model for our osmotic pressure to the data. And so what we say is that we are forming dimers or trimers, and then that we have sticky interactions that occur between all the components in the system. And we can calculate the activity. In this model, we're going to have to calculate activity coefficients, but we can calculate the activity coefficients within the Baxter model. And then there's also a solution for the Baxter model for a binary mixture of different size spheres, which we then used. And then, so with this model, you could actually reproduce the data pretty well, assuming either that you have dimers or that you have trimers. Now, this doesn't for sure show the existence of dimers or trimers. It could well be that you could use something like Wertheim's model, where you have anisotropic interactions and you're not forming closed oligomers, which could reproduce this data just as well. But this does provide one solution that seems to work well. And so then we just asked the question, well, how do we know, if you just look at the viral coefficient data at low protein concentrations, you don't see any curvature in the plot of your structure factor. So if you just measured low concentration data, you would never know that you have an anisotropic interaction other than from the fact that if you regress the tau to it, you'd find that for the system, it will probably be thermodynamically unstable at relatively low protein concentrations. But what we then did is we looked at this hydrodynamic function, which we could get from our diffusion coefficient measurements. And if you actually look at the hydrodynamic function, you would expect it to be relatively linear at low protein concentrations if you had non-specific interactions. But what you find is a lot of curvature in this hydrodynamic function. And so actually the hydrodynamic function that you measure by DLS for the system could tell you right away that you have anisotropic interactions. And in this case, we used the trimerization constant we got from fitting to the structure factor data. And then we were able to show that you could reproduce the hydrodynamic function, assuming that you had monomers and trimers. And so then this led us to look at, well, can you use DLS and SLS to look at whether or not you have anisotropic interactions and versus isotropic interactions. And so in this case, what we wanted to do is to interpret the diffusion coefficient measurements in terms of a chemical association model. And so in this case, you just write out your osmotic pressure. You assume that you have monomers, dimers, trimers. In this case, I just look at the case where we have monomers and dimers. And then what happens is your osmotic pressure reduces to this equation here. And then if you actually ask the question is, well, how do you define whether or not you have a dimer? If we only have, say, short-range attractions, I could always just say that my dimer corresponds to any type of configuration where you're actually sampling that short-range attraction. And if I use that definition of a dimer, then the only other contribution to my viral coefficient would be the excluded volume term. And so if I take that approach, then I can write the KD interaction parameter in terms of the excluded volume for the monomer. And then I get this additional term, which is related to the friction factor of the monomer over the dimer. And so if you look at this case for tangents for spheres, you can actually calculate what this 4F is equal to. And you actually find that this model perfectly agrees with what you would get for the Baxter model. And so if you just look at spheres and just say that you have dimers whenever you have short range attractions, you actually could show that this dimerization model gives you the same result as the physical association model. But the reason that we want to use it is that if you do have strong oligomerization, you would expect that this ratio of the monomer to the dimer, the frictional factors, is not going to be related to tangent spheres. So we might expect to see deviations from the model if you're actually forming, if you're not averaging over all your configurations so that it behaves like a sphere, and you have only a small subset of configurations that contribute to your dimer formation. And so here, if you look at what happens with a correlation, if your dimer has the same structure as the monomer, you get this dashed line. And here I show some data for KD versus B22 for that strongly interacting COA19, and you can see that it doesn't obey the correlation for spheres, whereas our weakly interacting system does. And so it looks like you can use this correlation to tell you something about whether or not you're getting anisotropic interactions. And then we wanted to use this to look at liquid-liquid phase separation. And so one thing we wanted to look at here is just to ask the question is whether or not you plotted your binodal curve in terms of the second viral coefficient, whether or not you got some sort of universal curve. And so Anna and Peter have, of course, done a lot of good work with lysozyme and crystallins in this area. And so we're kind of following up on that to see if we could do something similar with these different antibodies. And the approach we took here is we had 3 different antibodies, then we caused phase separation at low ionic strength solutions where we thought we'd have attractive electrostatics where you should have some anisotropic interactions. And then we caused phase separation at high salt concentration with ammonium sulfate, where we would expect that you have non-specific interactions, because when you salt out a protein, you should be salting out more or less a lot of the protein surface. Here I just show some measurements as a function of temperature. A lot of people have been fitting antibody phase diagrams to simplified models, fit phase diagrams, which have been measured in terms of temperature, but then it requires assuming a temperature dependence to your interaction potential. And here we just show that depending on the antibody and the type of precipitant you use, you get a different temperature dependence. And so that might not be a good idea. And so what we did is we measured the second viral coefficient as a function of salt concentration. We did it at low NaCl concentrations. So we got attractive electrostatic interactions under low salt conditions. And then we also measured the interactions in ammonium sulfate for the 3 different antibodies. And the viral coefficient profile is actually overlaid with each other, which is consistent with our hypothesis that we have non-specific interactions. And so we're also able to induce phase separation under these different conditions. And then we also compared this versus the KD measurements. And you can see that the B22 and KD for ammonium sulfate, you do get very similar profiles. But when you look at the low salt concentration conditions, you get a stronger attraction for COA19 when you look at the B22 measurements versus the KD measurements. And this is going to imply that, this antibody isn't going to follow the KD B22 correlation. And so we looked at this correlation, and it looks like we do have anisotropic interactions for COA19 at low salt conditions, but at the high salt conditions, it does fall on this correlation. And then also for COE, for another one for COE1, we also, at low salt, it does look like it's anisotropic. And then we measured the binodals in terms of salt concentration. And so we just looked at the phase separation at different salt concentrations, both for the low ionic strength conditions with NaCl and with the high salt conditions in ammonium sulfate. And because we measured the viral coefficients, we were able to determine the viral coefficient near to the critical point. And then we could also kind of map the binodals in terms of the viral coefficient. In some cases, we had to extrapolate the values. But the important point here is that we found that the phase separation does occur in a small window of the B22 values around -2 for almost all the systems except for COE19. And with COE19, you do have this very strong anisotropic or highly directional interactions. And one way of explaining this is just that when you're measuring B22, really what you're doing at low concentrations, you're just picking up this oligomerization equilibrium. And really what drives phase separation is going to be the interactions between the oligomers, which is not going to be picked up just in terms of this B22 measurement. And so you can also see if you can learn anything else by looking at the shape of the phase diagram. So we just plotted, look for some universal behavior by plotting the difference in the B22 from the critical point. You find that all the systems with sodium chloride that were precipitated at low salt have very thin binodals. And then the systems that were precipitated in ammonium sulfate have very wide binodals. We don't really know what's happening here. And this would take some additional modeling. One possibility for ammonium sulfate is that when you're precipitating the protein, the ammonium sulfate, the entire surface of the protein can interact. And so the types of clusters that can form are going to be very compact. Whereas in sodium chloride solutions, you have very anisotropic interactions so that you might form very open clusters between the protein molecules, and this might impact the thinness or width of the phase diagram. But the interesting point is that it doesn't really affect the location of the critical point. And then the last thing I just wanted to mention is how we can use light scattering to measure protein-solvent interactions. So protein-solvent interactions are usually characterized in terms of this preferential interaction parameter, which reflects the difference in the concentration or composition of the co-solvent around the protein relative to the bulk solution. So a negative value means there's a depletion of the co-solvent around the protein. A positive value means that you have accumulation of the co-solvent in the domain of the protein relative to the bulk solution. As I said earlier, from static light scattering, it depends upon this refractive index increment measured at constant chemical potential. This refractive index increment at constant chemical potential is related to the increment at constant molality, plus a term related to this preferential interaction parameter. In addition, you can relate this refractive index increment at constant molality to a term at constant concentration, and the refractive index increment at constant concentration you would expect to be relatively constant because refractive index is usually related to molar volume concentrations. And then you have this correction term to correct for the fact that one increment is at constant molality and the other increment is at constant concentration. But what this allows us to do is to use this refractive index increment at constant chemical potential. If we know this other one, we can then calculate what this preferential interaction parameter is. And so when you do light scattering, here what we did is we just measured this refractive index increment at constant chemical potential. And then we used this refractive index increment at constant chemical potential to calculate the molecular weight from our light scattering. And we showed that we could get relatively close to the monomer value. When you go to high excipient concentrations, you get very large deviations in this refractive index increment. It really begins to decrease. And so if you didn't correct for this effect, you would find that your molecular weights are very low. So the cool thing then what we did is, well, what we can say is like if you can do a size exclusion run and then have that hooked up in line with light scattering, when you do size exclusion chromatography, you know that you have your monomer protein coming off the column and it's at a very low protein concentration. So you're not going to have any contributions from your protein-protein interactions to your light scattering. And so what we did is we used this method. So instead of, we said we know what the molecular weight of the protein is because we know it's monomer. And then we can use, by fixing the molecular weight, we could then fit this refractive index increment at constant chemical potential. And then we could use this to calculate this preferential interaction parameter. And so this is a very kind of quick way of measuring these preferential interaction parameters. And so what we've done is we've measured this for 5 different proteins. And you can see that you get a lot of preferential exclusion around BSA, intermediate exclusion around some of the proteins, and the least amount of exclusion around lysozyme. And then we try to explain this. And so here what we do is we normalize this preferential exclusion by the surface area of the protein because you expect the preferential accumulation to scale with the area of the protein. And then these solid lines are kind of what you would expect if the protein just behaved as a low dielectric body. And so there's been some work that's shown that these predictions work pretty well when you have salts that don't interact with the protein surface. So something like sodium sulfate, you could actually predict the exclusion about the protein just by treating it as a microscopic air bubble. And so in the solutions with sodium chloride, you can find that you see that your preferential measurements actually do agree relatively well with this calculation, except for lysozyme with sodium chloride, you find the least amount of preferential exclusion. You do find that there is a weak dependence on the charge of the protein, so you get the least amount of preferential exclusion about the high isoelectric point proteins, and you get the most exclusion about the acidic proteins. And so we do find a correlation with the PI with sodium chloride. And then we looked at arginine chloride, which is a very common excipient. And it's used because people believe it accumulates around the protein surface. And so here is what you would expect if the protein behaved as a microscopic bubble. And in this case, you actually find that when you rescale everything by the surface area, all the preferential interaction parameters actually agree very well with each other, except for lysozyme. And so this is showing that the effect of arginine chloride is very non-specific, which is one interesting finding. The other interesting finding is that it does have less exclusion or even accumulation around lysozyme. And actually, arginine chloride was discovered by its ability to improve the refolding ability of lysozyme. And if you look at the amino acid content of lysozyme, it's actually very aromatic rich. And a lot of the literature suggests that arginine interacts with aromatic groups. And so we believe that these measurements are picking up those effects. And then on the last slide, the one interesting result, well, one thing that I think is quite interesting that we can do with this measurement is that if under chemically denaturing conditions, we can actually separate on a size exclusion column, we can separate the folded protein from the unfolded protein if we're using guanidinium chloride in our mobile phase. And then by fitting if we do light scattering on these peaks, we know one peak is folded protein, the other peak is unfolded protein. We can measure the preferential interaction parameter around the folded state and around the unfolded state at the same denaturant concentration. And those results are shown on the right here. And so this has never been done before. Generally, these preferential interaction parameters are used to look at the free energy of unfolding. So like the free energy of unfolding is related to the difference in the preferential interaction parameters around the unfolded state and the folded state. But when people do these measurements, they're measuring the concentration of the folded relative to the unfolded state. And so they can only measure this difference, not the values of each of these parameters. And so this is the first way of actually measuring these parameters for the folded state and the unfolded state at the same denaturant concentration. And then we can use this, and then we're just checking if we could then use this to calculate this kind of M value, which tells you how guanidinium chloride changes the free energy of unfolding. And so we compared it to what we would calculate from if we did this denaturant unfolding curve, and we find that we get relatively good agreement, at least for lysozyme, for these preferential interaction parameter measurements. So this approach could be quite useful in the future, first for understanding denaturant effects, but you could then potentially use it for understanding how other types of excipients interact with both the folded state and the unfolded state. So I think that's my last slide, so maybe I'll stop there. Thank you.